Hello, colleagues. I'm really glad to see you in our event. I'm Igor Bardowski. Today I have an honor to present new features of Woodwork for Inventor version 14. So let's begin.
The furniture design market is gaining momentum. Design trends are changing fast. New materials, forms, and hardware solutions demand creativity, flexibility, and speed from interior creators. Woodwork for Inventor is a solution that helps furniture design companies to stay on top and walk hand in hand with this evolution. Based on Autodesk Inventor, Woodwork for Inventor is built to meet every designer's needs and to strengthen design departments. By automating routine tasks, our software eliminates human errors and shortens time to design. Woodwork for Inventor is successfully used by more than 600 companies worldwide. There are two main reasons for this success. The technologies are developed one step ahead, based on 30 years of experience in the furniture market. A wide network of partners that ensures seamless implementation, integration, and support. We have a proven methodology for solving the designer bottleneck, avoiding painful sudden changes, large drops in productivity, and preserving the existing workforce. Our unique know-how allows us to solve the most complex problems, and the API gives us the opportunity to adapt Woodwork for Inventor to any needs. We guide our users step by step through the entire integration process, participating in all stages and providing all the necessary information to achieve your goals. Now we invite you to have a conversation about your business. Let's get in touch and see what gaps we can close at your company.
So let's begin from supported Autodesk Inventor versions. Of course, we support the newest Autodesk Inventor version 2024, as well as in the previous cases, we support two more versions below the current one, which is 2023 and 2022. So that's a good opportunity for upgrade. Now let's speak about the new features in the different areas of Woodwork, and let's begin from a design environment. So in the design department, let's start from the skeleton. In the skeleton, we have a new feature called Panel Array, which allows you to create an array of panels, as the name suggests, between two selected faces. Okay, so you can choose two faces and define how many panels you would like to get. There is a different scenarios for that kind of things. For instance, you can make the array of uniquely shaped shelves, like on this example, as you may see. Okay, in order to do this manually, you need to spend some time, but with this new feature, it's quite a rapid prototyping technology. So let's take a look at how it goes. So first, we begin from just a regular sketch. Okay, as you can expect, we can just design a general shape of this trapeze, define the depth, and then let's take a look at how this new function works. Okay, so normally we start from a concept, define constraints, then add some dimensions, and just a few minutes after that, that's what we have. Okay, so let's set the depth like this. Okay, set the panels all around, but except the front. Okay, now we can just hide some of the volumes that we don't need and use this new panel array feature. So as you can see, some of the panels now overlapping, but we can use trim function to just quickly trim the extending areas. Okay, and then we can use miter to just join the panels at correct angle, and that's it. So as you can see, after a few minutes, that's the model we got. Okay, very nice. Now let's speak about modified trim command. The command used to actually cut intersecting panels. Okay, so now you can specify the gaps between the sides or top and bottom of the selected panel. Okay, and moreover, there is a split option which allows you to split panel in two. Let's say we have some section in the middle of the furniture and the shelf which goes all the way from left to right. So we can use this divider in the middle to just get two shelves instead of one. Okay. So here you can see some of the example of what I meant. Yeah. So we have just a case with a vertical divider, and we got just a shelf split into pieces, two halves. Okay, let's take a look how it happens in real life. So, as usually, everything starts from the concept. I just speed up this step a little bit because there is nothing interesting in drawing the box. Then we can apply the panels all around. And as you probably know, we can apply the panels using the plane as a reference. Yeah? So we can make the panel in the intersection between the plane and the skeleton body. Okay, so now I can use the direct tool to just quickly set some offset from the front. Okay, that's it. But as you can see now, everything is overlapping. All the panels are intersecting, so let's just deal with that situation. I hide the back plate, and now I can use the split command using the plane as a split tool. Okay, so that's the work plane, and I got two shells, which is just split by the plane. They are overlapping right now. So let's take a look at what we can do at the next step. Okay, so I can trim this divider by the plane again, like this, but not in two pieces, not by half, but just using some gap value, which can be negative. So you can see now this panel going inside by certain value, like 9 millimeters, right? So we can do the same with the sides, like this. And now those shells just go inside of the vertical panels by a certain value, okay, like this. So for now, the panels are still overlapping, but we will deal with that a bit later. Okay, so now I can use a trim by a solid to just define correct join between the top and the side panels, like this, as we normally do. Okay, now let's deal with the shelves and the side. Okay, so I can select vertical panels as the panels to trim, now bonding elements. And here you can see that I can set the gap, yeah, like 1 mil all around, like this. Okay, and the same with this vertical divider. Okay, so let's choose panels that need to be trimmed, bonding object, set the gaps, and that's it. And so now we have the front view. We just flip the furniture, and that's the result. So we have nice grooves with some gap. Of course, this gap maybe is too big in this example, but just to have a clear vision of what happens, I just use this little bigger distance. Okay. So as you can see, that's quite complex geometry that was done in just a few minutes. Now let's pick another feature. It's like panel shrink option, which allows you to define different panel offsets. Yeah. So normally you would need to make a sketch to shrink the panel, do a extrusion with intersect option, but in this case you can do this in a single command. As you can see, the options allow you to select different edges and define different distance, okay, to shrink or extend the panel. Okay, what is the typical usage scenarios, like back panels, adjustable shelves? So you can see in this example that I just had the shell which was just inserted inside of the volume of the box, and then I use the shrink to ensure the front offset as well as the side offsets and the back offset as well. Okay, so let's take a look at how it goes. Okay, so I will not show the initial workflow. Let's imagine that we already have some box with the panels. Then we can just do the miter, and let's take a look at the back panel. Okay, so I can define the shrink distance like this, and now this panel became smaller. So now I can use a trim function in order to trim the panels which surrounds this back plate. Okay, and that's it. So you can see we have a nice groove. Just a few clicks. Okay, that's it. So of course, there might be different scenarios for this command. For instance, you can have a like cardboard panel in a group, maybe like some other scenarios. For instance, inside doors and so on. So you can do this in just a few clicks by selecting the panel you want to adjust and defining the offset parameters. Okay. Now let's take a look at the Edge DressUp command, which allows you to create solid bodies around the panel edges. Okay, so you can see that those orange panels, those orange pieces, those are solid bodies generated on top of existing door panel, which by the way, of course, can be done using shrink option. Okay, so first you make the door, then you shrink it down, and then you apply solid bodies around to make it like an inside door, like this type of door. Yeah, there might be different use cases. For instance, you can use a framing option. You can just have multiple steps in order to get like multiple frame all around. And let's take a look at how it goes. Okay, but before that, just one more word about the miter command. As you saw, this command allows you to just get a cut between the angle. There was nothing new here, but there's a new feature which allows you to actually extend the panels before a mitering operation, right? So you could do a miter if those panels would be overlapping in the previous version. Now, it's not necessary. We can do a miter in any case. Even if those panels are not overlapping, we can just automatically extend them and then do the miter operation. Let's take a look at how it happens, okay? But the typical scenario of this case can be like different kind of frames, solid wood doors, etc., right? So, the real case, okay? So let's say that that's our initial situation. Yeah, that's the panels. And let's take a look what we can do. Okay, so let's make the dress-up operation, define the thickness of the door. That's it. Now I can use the direct tool to move the solid body of the door a bit aside, because as you remember, there might be a gap of 2 mils between the body and the door. Now I can use the shrink command, the one we already saw. I can select all the edges, define the offset value. Let's take it bigger because we want to apply solid pieces all around. Now I can use edge generation command and define a bit smaller value because I need to have side gaps. Imagine that we can have multiple cabinets standing side by side, so I want to ensure the clearance. And then let's use the miter, which allows you to automatically extend the panels, actually make the miter. As you can see, there's the gap option that can be used for different purposes. Okay, so that's basically it. As you can see, we got the framing. Okay, now let's take a look at the interface. Okay, we have some new interface workflows. For instance, when you do body conversion and visibility change, visibility control, you can actually do this in a drop-down menu. Yeah, so you can say what you'd like to do with the object. You can say hide all the skeletons or maybe all the panels. And you do this in just a few clicks. You don't need to actually set the type and so on. You can select the item from the drop-down, and the operation menu will automatically inherit this option you selected, and you need to just pick the object that you want to actually convert or hide. Okay. Now let's speak about the hardware. That's one of the main improvements. Okay. So first of all, we built the new smart hardware mechanism, and later in the next slide I will explain what does it mean. But of course, during the insertion of the hardware, we need to recognize if it's like old hardware or the new one. Okay, and smart hardware recognition mechanism automatically recognizes the hardware made in this new way and applies some new certain rules to actually make the join in the correct way. Yeah? So for the user perspective, nothing changes in terms of usage of like legacy hardware, but when you use the new one, it actually works in a little bit different way. We will see how it actually performs, but it's very clear. Yeah, there is no user interactions needed. You just pick the hardware you want to use, and the system automatically recognizes if it's done in the old way or in a new fashion and applies some certain workflow to insert this option. So now let's take a look at what actually this new smart hardware is. Okay, and in simple words is the set of components made with some logic inside. Yeah, and it controls how those components need to be connected. So in the background, what we do, we actually calculate the contact path, right? So we can estimate what is the surface area, right? And in the logic of the hardware item, we can define the offset. So we can say that the first component should be set at some distance from, let's say, from the top. The last one should be at some distance from the bottom. And there should be one more in the middle, right? And using this logic, we can actually program our set of hardware items, build some logic inside, and we can actually place multiple instances of the hardware in the correct places in very short time. Later we will see how this happens. On top of that, hardware items can have some macros. Yes, this is not like a completely new feature, but just to refresh your knowledge, I will speak a few words about that. So some hardware requires to have multiple steps in order to be positioned. Say, for instance, you do a milling operation, then you do drilling, maybe drilling from the other side. And this actually requires multiple steps done in certain order, in certain tools, with the certain tools, to actually make a void for certain hardware, right? So you can make a macros, which actually not limited by 2.5 axes. It can be wherever, how many axes you'd like to use. It's up to you. What we do, we just pass the coordinates in a macro with the actual code of the program. Yeah? So we just run some application in certain position from the edge. So how it relates with this new smart hardware? Those hardware elements you design can also have macros inside, right? So not only that you place multiple elements in a single operation very quickly, there is no more work planes needed. Everything can be guided by embedded logic, but also those hardware items can be quite complex. Yeah, they can have multi steps needed for actually placing the elements. Okay, so now let's finally take a look at this command, how it goes in a real case. So you can see that it's like quite unusual shape, yeah. And we will place the hardware elements using regular attach command. So now we navigate in the new smart hardware folder, choose the lamella joint. And what I need to do, just select the items that need to be connected. Okay. Now the calculation happens in the background. We actually calculate the intersection area. Okay. And we decide how many of the lamellas must be inserted. And that's the magic, that's the trick. So as you can see, there is no need to make a work plane, there is no need to make some additional geometry. Moreover, you can embed like different scenarios inside of your hardware set. You can just work it out with different joint types and so on. Right? Okay, now let's move to the BOM, to the bill of materials. Okay, so we included some keywords, like for instance CoverWorkpiece.X.order, which allows you to actually define the order in which the cover will be applied. Okay, this is useful in case when you work with some expensive materials, or maybe if you use not a regular edge band, but maybe some thin metal plates and so on. In this case, the order can be critical. So Woodwork allows you to actually get this order. Okay. And speaking about the keywords, there is multiple keywords in the new version. Some of them just reward legacy keywords, some of them are new. So that's why we have a keyword help, which allows you to actually get the definition of the keyword in a easy to understand form with example and the format definition. And you can just use those keywords to shape the output data. Okay, so for instance, you can make the BOM, bill of material, actually tailored to your needs. So next topic is the materials. Okay, so in a material command, the first thing you'll see is new defined material assignment window. And probably there is no need to explain where's the difference. Yeah, but if you didn't notice, there is no more drop-downs. In most cases, there's some drop-down for certain material cover option, but nonetheless, there is no drop-downs, which means that there is way less clicks. Yeah, so you can just directly say what type of material you would like to assign and what is the option of this material assignment, right? On top of that, you can also see the thickness of the cover material you are applying. Okay, let's move to the next topic. This will be a CNC. Okay, so one of the new features is an option to export CAM technology into BOM. So how it goes. In the first step, you prepare a Woodwork technology as you normally do in a regular case, right? So then in the Woodwork BOM, you can actually use some certain template, XML template for a BOM export. And this BOM template can actually get the technology of Woodwork, right? So let's take a look at this as what the BOM does. It generates some output file. Yeah, it can be like a text file. So what we do, we request the Woodwork BOM to actually take the technology from Woodwork parts and just provide some document. And this document can be, say, in XML format. Yes, this file is built from CNC technologies within the parts of Woodwork, and this XML document can be imported in supported apps. So that's how it goes. Okay, so there is minor post-processor improvements under the hood. It's quite hard to explain what was actually done here and there in different post-processors. So, but there is one important thing. There is an option which allows you to build your own custom post-processor. We'll speak about this a little bit further. Okay, so when we do CNC, there is an option near the mill command that allows you to chip the area. Why we actually need to make the chip during the mill? So in most cases, when you do a milling of some contour, let's say cut out for a kitchen sink, you just go around the contour and the remaining piece just falls out onto the machine. Depending on the structure of the machine, this can be potentially dangerous. So say if you have vertically mounted plates, panels, so it's not good if this big piece of panel will just fall somewhere. So what you can do, you can just chip this panel. Yeah? So you can go around the contour starting from the center, actually turn the panel into the dust. So let's take a look at how it happens in real case. Okay. So that's the milling operation. Okay. And that was the option to actually chip the panel. So as you can see now, the router moves the milling tool starting from the center and moving towards the perimeter. In such a way, you just basically get a lot of chopped wood, and that's it. You have no damage to the vertical machine, or maybe some certain kind of machines that doesn't like when the big piece of wood just fell off somewhere inside of the machine. Okay, so now let's take a look at the nesting. Okay, the optimal layout. So in some cases you need to actually simulate what happens in the nesting, and we got you covered this in this case, this version. So now you can run the processing simulation on the nesting. Yes, so the nesting is not the same as just a regular CNC, because there are certain rules applies, there are certain restrictions. For instance, you cannot access the side operations. You basically do only the top operations. And since you do this with the rotary tool, which cannot make, like, say, sharp internal angles, in some cases you need to check what will actually happen during the nesting. Maybe you need to get some further processing on the CNC machine, maybe not. So as you can see, there is a nesting environment, and you can use right-click in order to simulate the processing. That's the last option in this drop-down. And you can do this on the sheet basis. Yeah, so you can select the worksheet you want to simulate, and it will show you the result. Okay, let's take a look at how it happened. So that's the nesting layout, and let's take a look what can be done. Okay, I can choose the simulate option, and that's it. That's the operations that goes on this worksheet, and you can compare it with what you expect to see. Yes. And if those results are correct, that's it. So we can just run this program in a real scenario. Okay. So speaking about the nesting and the CNC processing, the critical place is taken by the contours, by the contour processing. Because what is the machining is the right contour passed to the machine and right tool selected. Right, that's it. So for some machines, there is some legacy workflows or some special workflows usually used for certain contours, and usually those contours are applied on the pocket operation. Yeah? The CNC machine wants to use their proprietary mechanisms in order to just get the things done in the right way. So what we have here, we have an option to actually save the original contour, not an offset contour, but original contour as well. Yeah. So in this example, not just those red lines, but this blue contour as well. And the machine itself can decide what to do. Use our software path or calculate its own path. Okay. Let's move to the next topic then. The API. Application Programming Interface. So what we have here, we have included multiple APIs in order to make the possibilities of Woodwork more tailored to the customer needs. Yeah? Some of the customers already try to program some functionality. Maybe they need to extend existing functionality of Woodwork and so on and so forth. There's different scenarios, different cases why they may need to use some API. So let's take a look what APIs we have presented. So the first one is an iBox API. This allows you to make your own personalized application using iLogic or C# for arranging and customizing iBox components based on your specific needs. Okay, let's take a look at the example because it will be easier to understand. So we start from a simple cabinet prototype, and we want to control its dimension. And change maybe the amount of drawers, change the height, and so on. And when we run the form, as you can see, there's different options available. Okay, so we can say if you want to have a drawer or not, like this. And the system automatically updates the structure and actually puts the iBox element and do all this refresh operation in the background. Right, because we need to calculate the size of the iBox item. So when we change the parameters, the iBox automatically adapts to those changes, like this. say we can control this, the height, the depth, and other criteria of the cabinet. Okay, and in the background, everything rebuilds. So there is the triggers mechanism that allows you to actually see if the update of the iBox is needed. So in the iLogic form, you choose the configuration you want to use. Okay, and the update happens automatically. So you can choose different type of elements, different types of the iBoxes. In this case, those are different kind of drawers, and the system automatically responds to those changes, right? So you can see we have a different kind of drawers, different sliders, different rules, and that's basically about it. Okay. Now let's take a look at the material API. When we work with the materials, there is different steps, and we start from the material assignment. And speaking about the material assignment, the API allows you to define your own material assignment way. And if you like, you can even design your own custom application to do this. Potential usage scenarios can be different configurators, right? If you have like standard range of products and you want to have just different facades, so we got you covered. One important subtle thing here is that we allow to not only change the material, like say one laminated panel to another laminated panel, but we allow to change the material type. So we can say instead of a laminated board, we would like to get just HDF panel, high density fiber board covered by veneer. Okay, and the bond structure will change accordingly. Let's take a look. Okay, so that's the example. Okay, so we can change the size of the cabinet, and according to the rules, maybe we want to add another door, right? And that's the point when we start to change the color configuration. Yeah, so we can change the facades, for instance, in this example. Okay, and let's take a look at the BOM, because it's not only about the material color, it's mostly about the BOM. So here you can see we have a MDF and 4 PVC edge bands all around. Okay. So let's just try to remember the structure. 4 PVCs and 1 main panel. Okay, let's close it down. Go back to main assembly and change the structure. Yeah. So in this case, instead of using like a laminated panel, we can choose a veneer panel. Yes. Now let's open this standalone piece. Go to the BOM, and what we see, there is no more 4 pieces, there are 6 pieces of veneer because we have front and the back part as well. And so the API allows you to not only change the let's say one color to another one, yeah, but it allows you to also change the type. Okay. Moreover, you can also change the grain direction. Okay. Just go back to the main assembly. It was not correct place to do this. Let's do this on the main assembly, like this. Okay, and the grain direction changed. So now if you take a look at the BOM, of course, those length and the width values will be different. Yeah? So we just swap the length and the width, because let me remind you that the length of the workpiece is calculated along the grain direction. Yeah? So if you change the grain direction, it automatically changes. So you can see the first line says that the length is 796 millimeters, but this is the length of the final board. So the next line, right door workpiece 1, is actual length of the workpiece. So the size of the final part is calculated by longest edge. But the size of the workpiece, as you can see, the length is smaller value than the width, yeah, because we calculate the length along the grain direction. And when we cut the workpiece out, then we just measure the final part by the longest dimension and we treat it as a length. But before that, we measure the length across along the grain direction. Of course, if you want, we have an override option which allows you to choose if you want to follow this rule or if you want to always go along the longest edge to treat this as a length value. Okay. Now let's speak about the material replacement API. We spoke about the material assignment. Now let's speak about the material replacement. So what material replacement allows you to do? It allows you to map the model data with some external database using your custom application, right? And what it allows you to do in the workflow, it allows you to actually have all those materials you may request from your supplier in a few clicks, right? And when you set those materials from your enterprise resource planning system, the model refresh the appearance and look as it should. Okay, so that is the example made by one of our clients. Yeah, so they use the ERP system called Monitor, which allows you to retrieve material names and codes. And once modeling stage is complete, user can request material data from the ERP system, and information from the ERP system will be combined with the model dimension, and in such a way you get both, correct codes, names, and as well you get like correct amount of material, right? So as you can see, we just actually filter the material by the name or code. And there is custom-made like tabs that allow you to choose material type. Okay, so that's it. That's the model. We can actually generate the final report based on that newly refreshed material set. Okay, so if you expand the materials, they will get new codes and names, say oak or pine or balance paper or whatever else. Okay, so let's speak about the other things. There is a lot of new features under the hood, which is not visible by a naked eye, and you need to actually compare the pieces of code to understand what is going on. So we work hard on the algorithm improvements. We refined UX and UI in many places, some major tweaks. Of course, we worked on the bugs, tried to eliminate as many bugs as possible, work on performance optimization, and many more. Okay, so that's the main features of Woodwork for Inventor version 14. Of course, you may want to ask some additional questions, so we're always open for discussion. So you can contact us and actually have a personal discussion about something which is more critical for you. Thank you very much for joining our event, and see you next time. Good luck. Bye-bye.